Good day, everyone. Today we will be discussing one of the most important topics in this course. It is the topic of maximum likelihood estimators, which are arguably the most important estimators in this first part of the course. Maximum likelihood estimators are the most popular estimators in non-Bayesian estimation theory. In fact, it is very likely that if you have worked with deep learning, you have used maximum likelihood estimators. And their popularity can be ascribed to the fact that there's a straight path to derive them. So no complicated theorems or procedures to obtain maximum likelihood estimators. And besides, they are warranted to exist except in degenerate situations. But these benefits come at the cost of lack of performance warranties for finite data records, right? So, in particular, the maximum likelihood estimators may be biased. However, it can be shown that they asymptotically attain the Cramer-Rao lower bound as the number of samples goes to infinity, right? And this is a very remarkable property, of course, right? Because if our n is sufficiently large, then we can be sure that we are doing a decent job, okay? Of course, this holds under certain conditions that need to be checked every time. And although there are no warranties, typically these estimators work reasonably well, even for finite data records, right? So the combination of these properties is what motivates really why we use maximum likelihood estimators so much in practice. To understand what maximum likelihood estimator is, it is essential that we review what we learned about the likelihood function. In this slide that we saw before, we said that the PDF can be looked at from two alternative perspectives. So on the one hand, the PDF indicates or provides the probability that a random variable takes approximately a certain value. But on the other hand, we said that for fixed values of the observations, the PDF also indicates how likely is each value of the parameter. And that took us to define the likelihood function in this way as a function that assigns to each value of the parameters a quantity that can be interpreted as the evidence that the data provides to support that specific value of the parameter. And we provided a few examples, and this figure was presented to show the likelihood function of a set of independent Bernoulli random variables with the same parameter beta. So each of these figures corresponds to a different number of samples. So the first observation was that given this interpretation of the likelihood function, the data supports certain values of the parameters more than other values, right? And we also see, or we also saw that the more data we had, the more concentrated the likelihood function is around its maximum, right? So in this case, for instance, we have many samples, and we see that the evidence is concentrated about a small set of values, right? So specifically around this maximum point. So it is natural to expect that the true value of the parameter lies somewhere near this maximum, although we haven't formally proved it, but it is what intuition suggests. Therefore, it makes sense to use the maximum of the likelihood function as our estimate, and this is precisely what maximum likelihood estimators do. To formalize this notion, we consider the same problem as before. We are given data that adheres to a probability distribution parameterized by a vector theta that lies in a parameter space capital theta, and the goal is to estimate precisely theta. The maximum likelihood estimator is nothing but the value of theta in this parameter space that maximizes the likelihood function. This definition is quite simple and easy to understand, but in practice we prefer to maximize the log likelihood function instead. And of course, the solutions to both of these problems are equal, and the reason is that the logarithm is an increasing function, and therefore it doesn't change the location of the optima. Okay, so why should we use a logarithm? Well, the reason is twofold. On the one hand, the logarithm decouples products as sums. So this is very important, for example, in the case where the samples are independent along n. Remember that in that situation, the joint PDF of the data can be expressed as the product of the marginal PDFs of each sample. And therefore, this is the form of our likelihood function as well. When we take logarithms here, right, this product just becomes a summation, right? And this simplifies the process of finding the maximum meaningfully. On the other hand, the logarithm also simplifies the optimization process when the data adheres to a distribution that is in the so-called exponential family. The exponential family is a family of distributions that contains most of the common distributions, such as Gaussian, exponential, Bernoulli, Poisson, and all those distributions are in the exponential family. And they have the common property that their PDFs or PMFs can be expressed as the exponential of a simple function, and therefore the effect of this log is to bring down that function from the exponent down into this the objective function, and therefore the optimization process is also simplified significantly. Let us put this into practice by finding an estimator in this simple example. suppose that we are given a collection of exponential random variables that are independent and that share the same parameter lambda. So the goal is to estimate lambda given the samples x. The first step is, of course, to obtain the likelihood function, which, remember, takes the same values as the PDF of the data. And due to independence, the PDF of the data can be expressed as the product of the marginal PDFs of each sample. Now we just need to recall the PDF of an exponential random variable, which takes this form, and just by applying simple mathematical operations, we obtain the desired expression for the likelihood function. This figure shows the likelihood function where we can see the maximum likelihood estimate, which is at the maximum of this curve. But instead of maximizing this function directly, we said that we typically prefer to take a log and maximize the log likelihood function instead. So taking logs here, we just obtain this expression, right? And therefore the maximum likelihood estimate is the result of maximizing this expression over all non-negative lambda. And remember that the parameter of an exponential random variable has to be positive, and this is why we need this constraint. To find the maximum, we take the derivative of the log likelihood function with respect to lambda, and this brings us and set it equal to 0, and that takes us to this equation here. So if we solve this equation, we find that the maximum likelihood estimator of lambda is n divided by the sum of the samples, right? Since all the samples are non-negative, right, this denominator is non-negative, and n is also non-negative, right? Therefore, this estimator will never take negative values, right? And therefore, this constraint is satisfied by this solution, and we don't need to think more about it, right? So this can, of course, be written as 1 divided by the sample mean or average, just by moving this, just by dividing numerator and denominator by n. Okay, so this estimator really makes sense, and the reason is that if we remember from probability theory, the mean of an exponential random variable is precisely 1 over lambda, right? So it makes sense that the maximum likelihood estimator is 1 over the sample mean, okay? And to remain faithful to our traditions, we will also look at the example of estimation of a DC level in white noise. In this case, and unlike the previous lecture, we need to assume, or we assume, that the noise is Gaussian distributed, right? We cannot go ahead without knowing the distribution of the data, because we need the likelihood function to obtain the maximum likelihood estimator. The first step is again to obtain the likelihood function. I think that at this point we can all write the PDF of a multivariate Gaussian distribution with our eyes closed, right? Therefore, the log likelihood function is the logarithm of this expression, which comprises these two terms. The first one comes from the exponent and the second one from the denominator. To find the sought estimator, we need to differentiate the log likelihood function with respect to a, right? And since the second term doesn't depend on a, we just need to take the derivative of the first term, which, applying the chain rule, yields something like this. And just by upon applying some simplifications, we obtain something like this. Now we just need to note that the inner product between the vector of all ones and the data vector is just the sum of the samples, and that sum can be obviously written as n times the average or sample mean. And it's also easy to see that the inner product between the vector of all ones and itself is n, right? Because these vectors have length n. Now we can just take n outside and set this equal to 0 to obtain this equation. Solving for a gives us therefore the maximum likelihood estimator, right? So here obviously a needs to be equal to this sample mean, right? And therefore we recover an estimator that we have already seen in previous lectures. In particular, we saw that this estimator, the sample mean, is the MVU estimator for this problem. It's actually efficient, and it is also the blue estimator. Therefore, whenever our noise is Gaussian and we use the sample mean as an estimator for DC level, we have a triple theoretical support, right? Because this estimator is the MVU estimator, the blue estimator, and also the maximum likelihood estimator, as we just saw. Now, instead of estimating A, what we are going to try is to estimate sigma square, right? The variance. So this is the first time we estimate a variance in this course. And by now we will assume that A is given. Later we will see what to do if A is also unknown. As always, the first step is to find the likelihood or log likelihood function. The PDF is of course the same as before, but now the log likelihood function is no longer a function of A. It is instead a function of sigma square, right? Because this is the parameter that we want to estimate. However, it has the same form as before because it also results from taking logs in the PDF. To find the Ml estimator, we need to compute the derivative of the log likelihood function with respect to sigma square. Okay, and this just taking the derivative here yields this expression, where here we note that this term and this term need to be differentiated with respect to sigma square, not with respect to sigma. Okay, so this is because the parameter is sigma square. We could have also thought of estimating sigma, but our goal here is to estimate sigma square. Okay, so just not to get confused with the notation, This time we will substitute this sigma square with a dummy variable alpha and take the derivative with respect to alpha. After doing so, we have to replace alpha back with its value sigma square. Okay, and the same will be done for this logarithm over here. The derivatives of this expression in brackets can be readily computed, right? It's high school math, and we just need therefore to replace the alpha with sigma square, which yields this expression here. Now one can take the common factor out, this 2 sigma square, 1 over 2 sigma square, right? And this leaves us with this equation, okay? So solving this equation for sigma square yields that the maximum likelihood estimator of sigma square is this squared Euclidean norm divided by the number of samples that we have observed. Just let us frame this expression given its importance, but to interpret it, let us express it in scalar form. Okay, so just by recalling the definition of an Euclidean norm, we see that this is just the sum of the squares of the entries of the vector inside, right? And therefore it can be written in this way. This expression resembles the definition of the variance, right? Specifically, if we replace this 1 over n times this summation, if we replace this with an expectation operator, we find exactly sigma square. So this is very common, right, for an estimator, that it simply replaces an expectation with an average, okay? And this essentially corroborates or supports this estimator, right? Because we see that, as we know from probability theory, averages tend to their expectation counterparts, right? And therefore, for sufficiently large n, this will be very close to the true sigma square, right? And therefore, this agrees with intuition, okay? Now, as promised, we will look at the case where we want to estimate both the variance and the mean simultaneously, right? So none of them are given as opposed to the previous examples, okay? So this is formulated in terms of our notation as estimating this vector of parameters, which comprises a and sigma square as its entries. The log likelihood function is now obviously a function of both a and sigma square, but it has the same form as before because it is just the log of the PDF, and the PDF is the same as in the previous examples, okay? To maximize the log likelihood function, we need to set the gradient equal to 0, right? And remember that the gradient just contains the partial derivatives with respect to all the variables, okay? So this is not something that we need to compute now because we have already done it in the previous examples, right? So 2 slides ago, we saw that this derivative is given by this expression, and in the previous slide, we saw that this derivative is given by this expression, right? So we just need to set this equal to 0, which leaves us with a nonlinear system of equations, right? With two unknowns, namely a and sigma square, and two equations. Okay. So to solve this system, we just look first at the first equation. Here we see that it involves the product of two quantities that must be 0. Obviously, one of them at least needs to be 0, right? Since this one cannot be 0, then this has to be 0, right? As we have done before. And this means that the A solving this system needs to be of this form, needs to be equal to x bar, the sample mean or average. So now that we have obtained this value of a, we can just substitute it in the second equation. Okay, so we obtain precisely this. Okay, so now we just need to solve this with respect to sigma square, and by the same logic, this term has to be 0, right? And that leaves us with this solution. Okay, so this is the same as before, remember, but now here we have the maximum likelihood estimator instead of the true A. Okay, so remember that in the previous example this was true A, but now we don't know A, so what we have to do is to put the maximum likelihood estimator. And again, this can be expressed in scalar form to ease the interpretation, and this again is quite intuitive, right? Here we have remember the definition of a variance. Here we would have the expectation, and here we would have the expectation of x. Now, this AML is not the expectation of x, but it is its sample mean, right? And the outer expectation has been replaced with sample mean, right? So again, it is intuitive. And once more, thinking of this asymptotically, it's very useful. This is the asymptotically, we said that this sample mean converges to the expectation of x, right? And this sample mean here will bring us to the true variance, right? So this is not a rare case. Maximum likelihood estimators are typically very intuitive, as we could see in this and the previous examples. It is remarkable to say, though, that this estimator is not unbiased, right? So the estimators that we have seen before were unbiased, right? But this one can be shown to have a non-zero bias. This is done in a homework. But there is a simple way to scale it so that it is so that it becomes unbiased, right? In fact, MATLAB has these two options to use whenever we use the var command. One implements this expression as is, but there's another possibility in which it will implement just this expression, but with this n replaced with n minus 1, and that will effectively reduce and set the bias equal to 0. Now let's discuss how we can estimate the parameters of a Gaussian linear model. So remember from the previous lectures that in the Gaussian linear model, our data is a linear function of the parameters plus noise, right? And here we will be assuming that the noise is white, okay? So this matrix H is n by m, where m is the number of parameters, and it is assumed full column rank without any loss of generality. Okay, so the problem is given x, h, and sigma square to estimate theta. The PDF is, obviously comes from the fact that x is Gaussian distributed with this mean and this covariance, right? We have done this before, so it can be expressed in this way. The log likelihood is therefore the logarithm of this, and comprises these two terms. This one comes, the first comes from the exponent and the second from the denominator. To find the maximum likelihood estimator, we take the gradient of this log likelihood function, which applying the chain rule yields something like this, right? So this term doesn't depend on theta, so it is ignored. Just by simple mathematical manipulations, we can see that this gradient can be expressed in this way, right? And by setting it equal to 0, we conclude that this first term has to equal this second term, okay? And since H is a full column rank, right, it follows that H transpose H is invertible, right? And therefore, this theta, the solution to this equation, it can be written as H transpose H inverse times this left-hand side, okay? So this is precisely the same expression that we found in the previous lectures when we derived the MVU estimator and the blue estimators for the Gaussian linear model, right? So now we know that this estimator is also Ml, right? And that provides further theoretical support whenever we want to apply it in a practical situation. But not only does this estimator hold the honorary degrees of being Ml, blue, and MVU, it also coincides with the so-called least squares estimator, as we are about to see. So to this end, recall that theta hat ml is just the argmax of the log likelihood function, and for this model we saw that this function is given by the sum of these two terms. But since the second term doesn't depend on theta, we can safely disregard it. And by noting that maximizing the negative of a function is the same as minimizing the function itself, we obtain this simpler version of the problem, right? So this is a general optimization fact, not specific to estimation theory. The fact that this constant is non-negative also means that we can ignore it and instead minimize just this square norm, okay? So what we have found is precisely the definition of the so-called least squares estimator, which applies every time we have a model like this, right? So the Ml estimator equals this expression under the assumptions of the previous slide, right? So W has to be Gaussian, for example. And however, the least squares estimator is always given by this, right? And its closed form expression is, as we wrote in the previous slide, H transpose H inverse H transpose X, okay? So the nice thing of least squares is that it admits a nice geometric interpretation. So to see this, let us first replace this squared objective with just the norm inside the square. This is possible because what we are squaring here is non-negative, and therefore both problems have the same optimum. Okay. Now just let us express this vector here h theta in terms of the columns of h. Okay, so this can be written in this way, where we have also written theta in terms of its entries, which are the parameters that we want to estimate. Therefore, this vector is just the linear combination of the columns of H, right? And this can be interpreted geometrically by considering the subspace, or let's say a hyperplane spanned by these columns here, right? So in linear algebra, we typically denote by R of H this the set of all linear combinations of the columns of a matrix H, right? And this is referred to as a column span or range. But geometrically, it is a hyperplane, right? So since this term is noise, we typically think of this as the signal, right? And for that reason, we call this hyperplane, which is obviously a subspace, we call it the signal subspace, right? So the vector h theta is one of the vectors in this signal space. And however, the noise vector is not confined in any way to lie on this subspace, right? So it can point in any direction, and therefore x, which is just h theta plus w, is not generally on the subspace. Okay. So what the least squares does, as we see here, is to find the theta for which this vector h theta is closest to x in this Euclidean distance sense, right? So think that theta can be thought of as the coordinates of h theta, of this vector here, in the basis and defined by the columns of h, right? This is common linear algebra terminology, right? So we need to find the closest vector on this subspace to this given data vector. And just by, as we know, finding the closest point, on a plane to a given point is just a matter of drawing a perpendicular straight line that goes through that point, right? And the intersection between that line and the hyperplane gives us the closest point to this one, right? So since this straight line is perpendicular to the plane, we typically refer to this point as the orthogonal projection of this point onto the signal subspace, right? So this is a beautiful interpretation, of course, which always applies to least squares, but in this case, additionally, it applies to the Ml estimator, because as we said, the noise is Gaussian, and both estimators coincide. Okay, so this, as we said, theta. The least squares estimator is kind of more in general, although of course it will offer weaker warranties. But it can be applied anytime our data is given by this expression here. So as just by putting together what we have learned, as we expect that as we soften the assumptions, we also the guarantees that we have are also weaker, right? This is a common theme in statistics and in many other areas, right? So, for example, if we have a very detailed information about W, right? We know its distribution. In this case, perhaps W is Gaussian, right? Then we can apply maximum likelihood. However, in some cases we don't know the distribution, but we know the moments, right? The mean and the covariance, right? Okay, so in that situation we cannot apply ML because ML requires the PDF, right? But we can apply the blue, right? However, if we don't even know the mean and the covariance, at least we can go to least squares and we will obtain an okay estimator. Its warranties will be weaker, right? So the best linear unbiased estimator is, as the name says, the best among this class of functions of estimators, and therefore, in principle, it will be it will be better than just the plain least squares estimator, right? And the maximum likelihood estimator is by the properties that we are going to see, is asymptotically efficient, right? So that is much stronger, right? So we see that the more we know about W, we can come up with an estimator with stronger warranties. But at least it is good to know this one that can be applied no matter what. Now let us look at some of the most remarkable properties of the maximum likelihood estimator. One of them is that this estimator need not be unbiased, right? In fact, in one of the examples we have discussed, the Ml estimator is not unbiased, right? So this is different from the previous estimators that we have discussed in the course. Another remarkable property is that if an efficient estimator exists, then the maximum likelihood estimator is efficient under broad conditions, of course. But this is a really strong property, right? And its proof is quite straightforward. We just need to apply the second part of the Cramer-Rao lower bound theorem. Remember that under certain regularity conditions, an efficient estimator exists if and only if the gradient of the log likelihood function can be expressed as the Fisher information matrix times something that depends on x and not on theta minus theta, right? So whenever we can factor this gradient in this way, whatever we put here will be the sought efficient estimator, right? And this must hold for all values of x and theta, right? Therefore, it must hold in particular for this specific value of theta, which is the maximum likelihood estimate, okay? So one can just substitute this maximum likelihood estimate for theta in this equation, right? And that must hold true if an efficient estimator exists, right? So this is the expression that we obtain, right? And we just now need to note that by the definition of maximum likelihood of the maximum likelihood estimate as the vector that maximizes the log likelihood function, right? Its gradient is necessarily 0, right? So therefore, from this equation and the definition of maximum likelihood estimator, we conclude that this right-hand side has to be precisely 0, right? So now one can just note that the Fisher information matrix is invertible unless in degenerate problems, for instance, when the parameters are not identifiable, right? So since this matrix is invertible, this product of matrix times vector can only be 0 if this vector here is 0, right? So just by using that, we obtain that the efficient estimator must equal the maximum likelihood estimator, right? And this concludes the proof. As you can see, it's very simple and elegant. And another very important property is the so-called asymptotic efficiency, right? So remember that an efficient estimator is an estimator that attains the Cramer-Rao lower bound, which is given by the inverse of the Fisher information matrix, right? So for the maximum likelihood estimator, here there's a missing underscore, by the way, the asymptotic distribution, as the number of samples goes to infinity, is normal with mean the true parameter, okay, and covariance, precisely the Cramer-Rao lower bound, right? So this is also a very strong result. Another very important property that actually helps us out very often is the so-called invariance of the Ml estimator to transformations of the parameters. So let us assume, as always, that our data vector adheres to a probability distribution parameterized by a vector theta that takes values in a space capital theta, and the goal is to estimate not theta but a function g of theta, right? We have illustrated these kind of problems already several times in the course. And this function g takes values, of course, in the parameter space and returns values in the set gamma, and gamma is defined as the set of all possible values that g can take, right? This is the mathematical notation. This is referred to as the image of the set theta through the function g, okay? To analyze invariance, we will be considering two cases. In the first case, we assume that g is invertible, right? So, as we know, a function is invertible when there is a one-to-one correspondence between the elements of theta, in this case, and gamma, okay? So, whenever this is called invertible, because if we are given the value of g of theta, we can compute the value of theta that gave rise to it, okay? So to estimate this g of theta, we need a the likelihood function of g of theta, right? What is the likelihood of a value of gamma, let's say. And to do so, we need to actually define a new likelihood function, because the one that we have provides the likelihood of theta, right? And therefore we cannot apply it, right? So just by using our intuition, one can think that it wouldn't really make much sense that the likelihood of a certain value of gamma was different from the likelihood of the corresponding value of theta, right? So therefore it seems reasonable to set the likelihood of when gamma takes a specific value as the likelihood of theta taking the corresponding theta value. Okay. So this is the function, the likelihood function that we have looked at until now. The log of the PDF, right? I just use here this superscript theta to emphasize that it takes arguments of it expects values of theta as argument. Okay. So this expression can be written more generally in this fashion here, where we can plug an arbitrary gamma here, right? And therefore we just evaluate our likelihood function of theta at g inverse of gamma. Okay. Let's see how this looks in an example. Actually, in our example of a modified version of the example of the C level estimation, where instead of estimating A, we are interested in estimating this function of A, which is obviously invertible, right? This plays the role of gamma, right? And obviously, if we are given the value of gamma, one can immediately recover the corresponding value of A, right? The likelihood function of A is the same as we saw in the previous examples, right? And to find the likelihood of gamma, right, we just need to apply this equation here, right? And one can just, so we obtain that it is the likelihood of A evaluated at G inverse of gamma, right? And G inverse of gamma is obviously 1/3 of gamma, right? Which means that we just need to evaluate the likelihood of A when A equals 1/3 of gamma, right? And therefore we find this expression. So it is quite easy to find this likelihood function. Now we are ready to find the maximum likelihood estimator of G, right? Which clearly is given by the value of gamma that maximizes the likelihood, okay? So to express this in a more convenient way, we will be applying a standard optimization trick. So let's it says that maximizing an arbitrary function f of gamma is the same as maximizing this function evaluated at g of theta. And this holds whenever the values taken by the arguments of f on the right hand side are the same as the values of the taken by the argument of f on the left-hand side, right? And this is precisely the case, right? We have defined gamma to be the set of all the images of the points in capital theta through the function g, right? So this is obviously an identity, okay? And one can also relate the optimal gamma here to the optimal theta here, right? It is easy to see that they are related by this equation here. So, just applying this fact, we obtain that the maximum likelihood estimator of G is G of this expression, okay? So, now one can invoke or apply this equation here to conclude that this equals precisely G of the argmax of the likelihood of theta. Okay, so this was the likelihood of gamma. Now we have the likelihood of theta. Okay, and but now this should look familiar to us. This is precisely the maximum likelihood estimator of theta. Okay. So we have derived the invariance property. In simple words, it states that the maximum likelihood estimator of a function of a parameter equals the function of the maximum likelihood estimator of the parameter. Okay, so it is pretty simple to remember, and this actually simplifies quite a lot the derivations of maximum likelihood estimators. One example would be here, would be just the same as before, and the maximum likelihood estimator of A, remember, was the sample mean, right? We derived it in previous examples. Therefore, just by applying this expression here, we find that the maximum likelihood estimator of G of A, which was 3 times A, is 3 times x bar, the sample mean. Okay, so very simple, no additional derivation was required. Now let us look at the other case where G is not an invertible function. For instance, in our DC level example, we may be interested in estimating A squared, okay? So this is obviously a non-invertible transformation, because if, for instance, the value of G is 4, we don't know if A is 2 or minus 2, right? Therefore, many or more than one value of the parameter map into the same value of gamma, okay? So observe that here the parameter space contains all reals, but the image gamma contains only the non-negative real numbers. Okay. There are multiple possibilities for defining the likelihood of gamma given in terms of the likelihood of the parameters that are mapped into that gamma, right? The one used in ML estimation is the maximum of the likelihood of these values. Okay, so there would be other possibilities, right? One could, for instance, think of taking the likelihood of this plus the likelihood of this, right? But that would create mathematical problems, right? For example, it may happen that infinitely many values of the parameter are mapped into the same gamma, right? And if we therefore sum we sum infinitely many numbers that can be in general positive, right? We may end up in an infinite likelihood, right? And that would prevent us from obtaining the maximum likelihood estimator, right? So this is the way we define the likelihood of gamma, right, as this maximum, and it can be expressed in a more compact way in this way, right, where a prime here is our sort of auxiliary optimization variable, right? It is the maximum over all a primes that map into the specific gamma. So in general, so this was for this specific example. In general, the likelihood of a function g of theta can be expressed in this way, right? So the maximum over all theta primes that are mapped into the given value of gamma, okay? Just as a side note, I would say that in all these expressions, or many of these expressions where we are writing max, we should actually write sup as a supremum, but I decided to just write max just not to complicate things, because this course is intended to people with different backgrounds. So the maximum likelihood estimator of G is, as always, the maximum of the likelihood function. Okay. So in this case, we take this we have to maximize this likelihood function of gamma, right, which is given by this expression here, right? I just substituted this here. And by applying the same optimization facts as in the previous slide, one can easily conclude that this just yields a G of the maximum likelihood estimator of theta, right? So we found exactly the same relation as in case 1, okay? The maximum likelihood estimator of a function of a parameter equals the function of the maximum likelihood estimator of the parameter, okay? So it's again very easy to remember. In our specific example, we may be interested in estimating a squared divided by sigma squared, right? This is the signal to noise ratio, and we discussed this earlier in the course. Obtaining this maximum likelihood estimator is now very simple because we just need to write the maximum likelihood estimator of square it and divide it by the maximum likelihood estimator of sigma square, right? So again, it's very simple to estimate maximum likelihood to estimate functions of parameter using maximum likelihood. Now that we know the main properties of ML estimators, we are in a good shape to tackle more general and practical estimation problems. We will now be looking at the estimation of the mean vector and covariance matrix of Gaussian multivariate Gaussian distribution. And to that end, we need to generalize a little bit what we have seen so far. Remember that until now, we were observing a single number for every n, right? Our samples were scalars. However, in practice, we typically observe multiple numbers for each at each time instant, right? And therefore, it makes sense to form a vector that collects all those numbers, right? So this is the example, for instance, when we observe a phenomenon with multiple sensors, right? Think, for instance, of an inertial measurement unit which comprises 3 accelerometers and 3 gyros. It is used in all sorts of vehicles for navigation purposes, right? So therefore, at every time instant, an inertial measurement unit provides 6 numbers, right? And therefore, it makes sense to form a vector of dimension 6 and call it x bar underscore of n, right? So in general, we will have and this it will have dimension capital D, okay? And for this specific example, we will assume that its distribution is a multivariate Gaussian distribution. Therefore, its mean vector mu has to be d by 1, and its covariance matrix C has to be d by d. To simplify the notation, we will introduce this data matrix X, which comprises the vector valued samples as columns, okay? So therefore, X is of size d by n. The problem is, given this data matrix, estimate mu and C. And if we want to do that using ML, the first step that we need to perform is to obtain the likelihood function, right? In this case, the PDF is written as, or can be written as the product of the PDFs of each sample because of independence, right? And therefore, we just need to remember the expression for the PDF of a multivariate Gaussian distribution, right? So remember that it is the exponential of this quadratic form here, where this is the inverse of the covariance matrix, and in the denominator we have the square root of the determinant of 2 pi c. Here, I mean, it is very common that people write this 2 pi factor outside. Here, then it would be, it has to be raised to the power of d divided by 2, right? And however, I prefer to write the 2 pi inside the determinant, because then I don't make mistakes with that exponent, right? So remember this property of determinants. If you have a matrix that is n by n and you multiply it with a scalar alpha, right? The determinant is just alpha to the n, the dimension of the matrix, times the determinant of A, right? So therefore, if we write the 2 pi here, it comes to the outside as 2 pi to the power of d because of the determinant divided by 2 because of the square root. So this is just, I mean, a trick. You just can do whatever you want. And now one can apply the properties of the exponential, right, to get this product inside as a summation. and also operate the denominator, which becomes this function here. The log likelihood function is consequently the logarithm of this, right? And it can be expressed in this way. As always, this term comes from the exponent, and this term comes from the denominator. Now that we have the log likelihood function, the next step is to maximize it with respect to mu and c to obtain the desired ML estimators. Unfortunately, we see that such an optimization task is complicated by the presence of the inverse of one of our optimization variables. And this is where the invariance principle that we saw earlier comes to the rescue. This is what we will do to turn this problem into an easier one. The first step will be to, instead of estimating mu and c, we will start by estimating mu and c inverse. Okay? So C inverse will be denoted by capital S. Okay. So after doing this step, we will obtain the ML estimators of these two quantities, and to recover the ML estimator of C, we just need to invert the ML estimator of S, right? So this is just a plain application of the invariance property. And to this end, we need to express this or need to find the log likelihood function of mu and s, right? And this can be easily obtained from this expression. This first term here comes just by replacing C inverse with S, right? The second term is just a constant, and the third term involves this logarithm of C. Here we can note that the logarithm of C is obviously the logarithm of C inverse, and just by the properties of the logarithm, this is equal to the logarithm of 1 divided by the determinant of S, right? And just by the properties of the log, this is minus the log of S, right? Therefore, this minus log of C of the determinant of C becomes plus log of the determinant of S. So let's start by maximizing the log likelihood function with respect to mu. So we take the gradient with respect to this variable, which after applying the chain rule to the first term and noting that the other terms do not depend on mu, yields this expression. Now one can just cancel these constants and exchange the order of S and the summation, as well as writing the summation inside the parentheses. Note here that we need to multiply mu by n because we are adding it n times, right? So to obtain the maximum with respect to mu, we need to set this gradient equal to 0, and since this is a matrix and this is a vector, this is 0 only when this vector is in the null space of this matrix, right? And since this matrix is invertible by definition, its null space contains just the 0 vector, right? And therefore this has to equal the 0 vector. So from this expression one can solve for mu to obtain this the optimal point, okay? Therefore, the maximum likelihood estimator is just given by the average of the data vectors, pretty much as in the scalar case, in the case where our samples were were a scalar. Okay, so this will be denoted by x bar underscore, right? Bar, as always, denotes sample mean or average, and the underscore denotes vector, right? So it's just a generalization of the scalar case. It remains to maximize the log likelihood function with respect to S. And to that end, we will apply some mathematical manipulations to simplify notation. So first, note that this is a row vector times a matrix times a column vector, right? So therefore, this is a scalar. And a scalar is just a one-by-one matrix, right? And therefore, this matrix equals its own trace, right? So by applying the trace, the properties of the trace that we saw earlier, specifically the trace of A times B equals the trace of B times A, we can rewrite this in this way here. Okay, so now we have a matrix times a column times a row, right? And this is a matrix. One can then use the linearity of the trace operator to write this summation to the right of the matrix S, right? And just by defining f mu to be this sum divided by n, we can write this this expression in this way. Okay, so the reason of defining it with this factor of 1 over n is to simplify notation later. So therefore, this term equals this, and what we need to do now is to take the derivatives with respect to all the variables here and set them equal to 0, right? So instead of doing what we have done so far, which was forming a vector with all the derivatives, namely the gradient vector, here we will arrange the derivatives in a matrix, and that's just because it simplifies things a bit. Okay, so our matrix of derivatives can be written as in this way, right? So this is the first term. The second term does not depend on s, therefore it can be ignored, and this is the third term. Okay. Now it can be seen that this matrix of derivatives equals is given by this expression, and I leave it as an exercise. It is not difficult. You just need this property. If A is a matrix that depends on some variable alpha, then the derivative of the log that is given by this trace here. So to find the optimum S, we need to set this equal to the 0 matrix, and just solving for S yields that S must equal the inverse of F mu. However, here this doesn't directly provide us with the optimum S as before, right? Because this F depends on mu. So what we need to do is to put together what we know. That is, in the previous slide, we saw that for the gradient with respect to mu to equal 0, we need that mu be this sample mean, okay? And from what we have seen here, the derivative, the matrix of the derivatives is 0 only if S is the inverse of F mu, right? So this is a system of equations, and to solve it we just note that the first equation directly provides us with the value of one of the variables, right? And to obtain the value of S, we can just substitute it into the first equation into the second equation, and this yields that the Ml estimator of S is nothing but the inverse of F when mu is said to be this Ml estimator of mu, right? Therefore, we can so this was the first step in our procedure to apply the invariance property. The second step is, remember, to invert the Ml estimator of S to find the Ml estimator of C, okay? And therefore this estimator is just F mu hat Ml, okay? So to sum up, this can be just by substituting mu Ml here in the definition, here in the definition of F, we obtain this expression for the Ml estimator of the covariance matrix of a multivariate Gaussian distribution. So note that this is this generalizes the expression for the Ml estimator of the variance, right? Now, instead of having x minus mu Ml square, we have the product of this column vector and this row vector, right? That will give us a matrix, right? And the same interpretation as before applies, right? So here we have the Ml estimator of the mean, but if we knew the mean, right, then we just plug here the mean itself as in the scalar case, right? And one can also see that this estimator is biased, but asymptotically unbiased, and one can correct for the bias by dividing by n minus 1 instead of dividing by n. This brings us to the end of the lecture. Let's just recap some of the main messages. We defined Ml estimators as those that seek the values of the parameters that maximize the likelihood function. The motivation was the interpretation of the likelihood function as a measure of the evidence that the data provides to support a specific value of the parameters, right? We also said that the Ml estimator is extensively used in practice, despite the lack of performance warranties for finite data sets. Besides, it can be even biased. However, on the good side, it is efficient whenever an efficient estimator exists under broad conditions, and asymptotically attains the Cramer-Rao lower bound. Besides, we also discussed the invariance of Ml estimators. Remember, the Ml estimator of a function of the parameters equals the function of the Ml estimator of the parameters, right? So simple to remember, and it is very useful, as we illustrated with the estimation of the mean vector and covariance matrix of a multivariate Gaussian distribution. So at this point of the course, we know quite a bit about estimation theory, but the whole framework that we have considered so far suffers from a big limitation, and it is that it doesn't allow us to capture prior information that we may have about the parameters, right? So in practice, we typically have some idea about the values of the parameters even before seeing the data, and the current framework does not allow us to encode and exploit that information. And once we realize that we have these both these sources of information, prior information and data, we need also to learn how to balance them in an appropriate fashion, right? So we obtain estimates of the highest quality possible. This will be what the subject of the next part of the course, which starts in the next lecture. So this is all for today. Thanks for your attention, and see you in the next lecture.